Hey everyone, welcome back to Primitive Computing. Tonight we're picking up where we started off a couple of weeks back, but let's get back up to speed with where we were. So I took a couple of weeks off. I just kind of wanted to break and had some other stuff I was doing. But we're back, and I'm excited to get back into this. Um, yeah. So tonight, if you remember where we were last week, we spent a lot of time, more time than I was actually surprised it took as much time as it did. But so I'm scrolling through the code over here. We worked on being able to print messages or print a number on the screen. So basically, the way we call it is we move into our first register AX, the value we want to print. We call this function print number, and then here's the code for that. Um, we're starting to see some since we're using functions more, and we're going to rely on these a lot more as we keep going. We're seeing some kind of I guess some of the structures and things that you would see in a more, I guess, structured programming language show up here. And so we've got some things like saving registers upon entry to a function, and then you know down at the end of the function we restore those registers. And so what that's there for is to uh when you call a function, you don't want it to like just destroy the context of what you were working on. Like, that's the point of functions, is that they kind of stand alone. You can go over to them, you don't have to worry too much about the details of what they do. And all they do is they return a value back to you, or they do something and then they come back to where the execution was. um, However, when we're running the function, we want to use the registers that we have available to us. And I think we use just about all of the ones that are on the original x86 for printing a number last time, partly because there's like only about 6 or so general purpose registers on the original x86. The newer ones, like the x86 64, has got uh, quite a bit more registers, and I think we actually could use this here, but that seems like cheating. So um, because there's so few registers, we end up having to use all of them, and which is why we've got to save them so we can restore it. There's different ways to do this, and if you've ever looked into different calling conventions, that's basically what's encompassed in the calling convention. So, what registers do you use to pass arguments in? Do you pass arguments on the stack? What registers does the caller have to save, and what registers does the callee have to save? And so one thing that a lot of systems will do is, in this case, we've been doing basically the caller or the callee saves everything. What a lot of systems will do is they'll leave 1 or 2 registers, or 3 or 4, some number of registers they'll set aside as um, as call as caller save registers. And what that means is that if you're in the function like the callee, you can use those without worrying about clobbering anything for the previous calls. Um, we're storing them in like we're passing arguments through registers. And so one thing, like, we're using the AX register as our first argument. So here I actually did save it and restore it from the stack, but that would actually be a pretty reasonable thing to say, like, hey, all of the argument registers are considered caller save. And so if the caller doesn't need it anymore when the function is done, it doesn't have to bother saving them, and that can save you a little bit of performance. And so um, calling conventions, the most important thing they do is they make it easy to make sure that to make it possible for different functions to be able to call each other and pass arguments successfully and return values and all that. But then there's many different calling conventions, and one of the reasons for that is that arguably you can get better performance with some of them, because you can save basically like this boilerplate here. So this section where basically any point or any function that we end up writing is going to have a very similar first section to this. And this is considered boilerplate usually, or it's the epilogue and the prologue for the function. And a lot of the purpose of that is to implement the calling convention for it. And so each of these takes cycles on the CPU. It takes time to decode it. There's reasons for it. And so sometimes you can get better performance by making it so you don't have to do quite so much and to respect the calling convention. The important thing is that, like, or one thing about this though is that, like, basically you can cheat in this as long as you don't get caught. And so if we weren't using all of these registers, we wouldn't have to push them all to the stack at the beginning. But these are all registers that I ended up using, and so that's why we saved them all to the stack. Anyway, the way we print numbers is, just to do a bit of review here, is we pretty much, or we go through this loop and we divide our number by 10 each time. And then we push the value, like the single digit that we get by, or dividing by 10. So we do like, it's a div mod instruction. The x86 does div and mod at the same time. And so the mod gives us the remainder. So if we print the number like 42, the first time we divide by 10, we get a remainder of 2 with a quotient of 4. And then we take 2 and we push it on the stack. We add the character 0 to it to turn it into an ASCII character. And then we continue. The nice thing about pushing it onto the stack this way is we get kind of a last in first out thing, which is good because at least for us, for the way we write numbers, we like to have we like the most significant digit comes first. So 42, we write that as 42, not 24, for example. And so, but here we're computing it from the smallest digit to the largest, and so we need to have that in the right order. When that's all done, we jump down to this extra function called print stack. Not really a function, it's like another label, another block of code down there. And this just calls up, basically it does, a little bit of bookkeeping to put the cursor in the right spot. And then we call a BIOS interrupt to write the string on the stack to the current position on the screen. Okay. And then we get ready to exit down here, and which is just basically doing the reverse of what we did in the epilogue or in the prologue of the function. So this is our epilogue down here. This isn't really as exciting, especially if we've been doing Pong. Pong I think is a lot more fun to watch, but here's what it looks like when it runs. So we've got some code that's left over from our boot sector. I just put a hello message in there so we know that our boot sector actually ran. And then the number 42 shows up. So this is the one that we had passed as an argument. So this is going to be a really important feature because we, tonight we're going to build a prefix arithmetic calculator or make some hopefully significant progress towards that. And we want to be able to see the answer. And so to do that, we write out 42 at the end. Okay. So let me go over to my notes file here because I've been writing some notes. So today is February, whoops, I cannot type, 28th. Sometimes I think of this as March 0, just because sometimes math works out better that way, but I'll write it out as the way that normal people do. And so this one, our goal is just our prefix arithmetic calculator. I think if for some reason it ends up to be super easy and we get further, we might start adding some extra features to this simple language, but I have a feeling this is going to take most of the time because it's tedious doing really much of anything in a simple language. So there's some sub parts of that which are kind of left over from below, like the printing number, or we have printing numbers already, but we'll need to parse numbers. So some of the different aspects of this, the aspects are pieces of the solution. There's got to be a better way to phrase that. I'm not really sure what it is though. So we'll just stick with that. So our pieces for the solution are the things that we have to do basically. Let's call this our tasks. So one thing that we would want to do is eventually we want to read input from the user. So from console, I guess. We're not actually going to do this at first. And the reason is just because I don't want to. Basically, it can be kind of tedious. We're going to have to spend a lot more time like fishing for the right bias functions, like to read keys and all that. And I just, we've been doing a lot of that in the past. That's not really what I want to focus on tonight. Instead, I want to do something more computationally interesting. So we'll need some way to tokenize our input or parse our input. Parsing here is going to be very simple because as we talked about last week in prefix arithmetic, we have an operator and then we have numbers coming up. So One thing I didn't put in any of these examples here is 2-digit numbers, and so we want to be able to do that. So we want to be able to have you know whatever plus 42 and 12, and then this would give us 54 as the answer. Okay, oops, not 53, 54. That makes parsing a little bit more interesting because we can have multiple character things to parse, but that's that's okay. So tokenizing is basically just going to be returning what kind of thing we read next. And so in our case, we're going to have operators and operands, or operands, which are just numbers, like that. And then the last thing we need to do is to compute. We will probably sort of do these together, okay? Or at least the computation will happen as the tokenization happens. So it's not like we're going to run through and build a stream of tokens. We're actually just going to tokenize as we go. Okay. Cool. So I think one thing that would be helpful, probably for me, if not for you, is to write this out in a higher level language, because that'll give us a like sort of a template to follow. Okay. So so the idea is first we're gonna have, I'm not gonna show the get token function, which will be our parser. But get token is basically going to be it'll return either a number or the operator for and so I think what I'm going to do is numbers will just come back as let's see, returns numbers as numbers. So it'll just fill the return register with a number. Operators will be negative numbers. And so the idea is we'll have like, plus would be -1. I'm not going to put an equal there. Let's do a colon. Let's do, we'll do plus and times, I think. And so that'll be like -2. And that way we can have like a single return value that says whether the input was positive or negative, or sorry, whether we got a certain token out or whether we got a number. Okay. Cool. And so yeah, there's other ways we could do this. One thing about this is it means that we can't parse negative numbers, but I think we can live with that. If you really want to parse negative numbers, once we have like minus, we can do you can always do like minus 0, 42, and that's a way to get to -42. So it's not the end of the world if we don't support this. Cool. So then we're gonna have I'll call it eval. It feels like I should call it compute because that's what they called it up there. But an eval is basically going to be basically, I guess I'm using kind of like a Python-y pseudocode here. So we'll do we'll say like t equals get token. If t equals -1, then we do let's see, a equals eval, b equals eval, and then we return a plus b. Okay. Then we'll have else if t is equal to -2, then we'll do a equals eval, b equals eval, and then we'll return a times b. Okay. There's other ways we could do this, but I think this is probably just going to be simplest to like duplicate these calls to eval as we go. So we've got some recursion in there. And then the last thing we do is we say else, and then in this case we just return t. as a number. Okay. So that should work pretty well. It should be nice and short, which is a good thing for assembly language. And yeah, there we go. For parsing numbers, we're gonna have kind of basically we're gonna do sort of the reverse of what we did with printing the numbers. So we'll still have a loop of like, reading character by character, and then we will like multiply our accumulator by 10, and then we'll add the next digit, and then we'll continue as we go. We have to add some extra stuff to check for like spaces and white space and make sure we ignore that. One of the things that I'm going to do is just basically like hard code a constant as an expression that I want to test. And then that way we can avoid doing all of this like reading input from the console. And that's something that if there's time, we can add that in later. But anyway, so that's the plan for tonight. Cool. Okay. I should probably break these out into like different functions. Let me go pull my, do I have the NASM instructions? No. Okay, so I'm gonna go pull up my NASM docs and just make sure that, basically I think I'm gonna start breaking stuff out into different files, just to help me organize this, because I think it's gonna get really confusing otherwise having me scroll up and down, because we're at like printing a single number goes from like, we start at line 56 and end at like line 120, whatever. So this is going to get kind of unwieldy. So let me see if include is, yeah, here we go. Cool. Yeah. So it looks like we can just say include, and that'll be a lot more simple. I may find out how to do constants also, because that would be nice. Here we go. Whoops, not include binary, but we're close enough. Okay, so constants. Cool. Yeah, this actually looks really easy. So, yeah, that should be pretty simple. So, oh, times is kind of useful too, that I can do times to repeat data and such. So cool. I don't really want to rely too much on all of these little like tricks, because that means it's more stuff I have to implement later. So eventually I want to work towards being able to write an assembler that's able to reassemble this, all the code that we've written so far. And that's how we can get to a self-hosting system. But it's also kind of nice to be able to go faster now as we get started. So let me make a new file. And this is going to be, whoops. Okay, print number.asm. Okay. Oh, that was a weird sound that I just got. Here we go, print number. So we're gonna copy all of this. And we're going to say include print number.asm. Okay, so we'll try and do like one file per whatever, per function. That's the word I was looking for, per function. Cool. Okay, so let's write an example expression first. So let's say test case 1. And this is going to be, we're going to do some binary, and then maybe there's a trick here to do 0 strings also. I don't know, it seems like maybe not so much, but oh, here we go, character strings. Yeah, okay. So they don't really do I can do Unicode strings. That's kind of nice. Um but yeah, we'll just we'll just keep doing our own like manual zero terminated strings. So let's do plus 1 2 as the simplest one. Let's do this case. Oh wait, we need a 0 on here also. Let's do times 2 4 or 2 3 I guess. And let's get some double digit numbers. Let's say plus 1 2 3 4. And then let's see what else. Oh yeah, we actually want to do some nesting too. So let's do test case 4 is going to be you know, say times plus 1 2 plus 3 4. So this one will do kind of the opposite of the order of operations, where we want to do the two additions first. So let's take 3 and 7 and multiply those together. So we should get 21 out of that. I'm going to write the expected answers here too. So this is going to be 3, 6, and 46. And this problem's always a fun one to like see if I can do mental arithmetic. So then we have 3 times 7 for this one, so 21. So let's like align all of these nicely. Okay. You know what? I am just gonna call. Whoops, that's my reading. These are my notes. I am just gonna call this compute instead. Okay. So there's print numbers. We shouldn't have to touch that at all. Oh, I'm also gonna go down here and say add number. Cool. Okay. Okay. Sorry, I should think out loud a little better than I'm doing here. But so what we are doing now, I think I'm gonna work on the parse or the tokenizer, because that's sorry, let me readjust myself here. Because I think, you know, that's definitely the next thing that we'll want to do. So let's say this is get token. Okay. So for get token, I'm going to use two. I'm actually going to, okay, I'm going to cheat here and have two different things to do, basically. Yeah, I don't know. Yeah, so we're gonna have two functions. So basically we want some way to say which string we're using as our input. And so I'm gonna call a function I'm gonna have one function that's just like sets what we're using for the input, and then another function that actually does the parsing. So yeah, so here we go. So we're gonna have let's have our like buffer pointer, and then this is gonna be a word, so 16 bytes, and it'll just be 0 to start with. Okay, so then we'll have a function called set buffer. So set buffer. How do I do my usual kind of header on these things? Oh yeah. Let's see. So this that's the buffer used for tokenization. And then arguments is going to be, so AX is going to be the new buffer. Okay, So basically, all we do in here is say move into AX. Oh, we have to do like brackets around it, I think. And then return. So ret. We don't actually have to do all that prologue and epilogue stuff on this because it's just a single instruction, so we don't really have to do very much. We could, inline this function anywhere, and I think any real compiler would do that, but I think it makes more sense to do it like this, so that we get a little bit better, it's a little bit clearer, like what's going on and all this stuff, like what the interface works. So, you know what? I think buffer is a bad name. It's probably going to collide with other stuff. So let's say token buffer. We'll do this here as token buffer also. All right, cool. Now we can write get token. So get token. Man, cannot type. Okay, so returns the next. Okay, so this means -1 for plus, -2 for times, and n. Okay, and I'm not going to make this do any error checking because or like error handling, because I don't know, we're just going to assume that the programmer's using it right. The programmer's me, so I wrote it. I should be able to figure this out. Arguments, none. Okay. So interesting. I realized in our print number function I didn't actually add we didn't show a way to do subtraction on there. So maybe if we have to touch print number today, that's probably a good change to make. Sorry, what I meant by subtraction is negative numbers. We don't handle those well. Cool. So get token. So we're basically gonna say move into let's just use AL. Wait. Okay. So first we have to push AX. And then down at the so we'll have a label down here called exit, and that'll be pop AX and return. So I'm gonna try to so since we have this like prologue and epilogue stuff we have to deal with, I'm gonna follow a single return point discipline or like style, where we never just return from the middle of a function. We always instead do a jump to exit or go to exit, and then that will basically make it so I don't have to remember to duplicate the epilogue at every possible exit path for a function. I think most compilers actually end up doing something like this as well, because there's not really any point in duplicating code there, but sometimes it makes sense to have return from the middle or something like that, especially if the function doesn't need any prologue or epilogue, then you can just return from anywhere, but we're going to need that here. So okay, so we'll probably do some loops and stuff later, but for now we'll just try not doing anything. So let's see. So let's say we're gonna load into AL token buffer, and then let's see. We're also gonna add 1 to token buffer. So this is sort of we're going to keep advancing like, pointer by pointer. Okay. So let's see, let's add some comments to say what's going on. So read first character and advance. Buffer 2. Okay. So we actually can start testing for a couple of things now. So the first thing we want to do is we can say compare AL against let's see. Let's see. Oh, yeah. Against plus. Check for plus. And then we can say JNE to check mole. So if it's not a, so we'll check first for a plus. If it's not a plus, then we will check for multiplication. But if it is, then we will say move into AX -1 and jump to exit. Okay. There we go. Check mole. This is pretty much exactly the same thing. So we have, now we check for a star, and if it is a star, oh yeah. This is where I was going to do my constants too. So let's see. So well, token add is going to be equal to -1. Token mole is going to be equal to -2. Actually, you know what? I'm gonna put this over in our boot.asm. So we'll just put all of our constants there, and then this is going to be the main program. Okay, cool. In this case, we're gonna return token add, and then this will make it much easier to read. But it's jumping the check mole, this will be check num. So then, let's see. So check num. The first thing we'll do then is we'll compare AL against 0. If it is less than 0, we know that it's not a number. So we're basically just going to have this ignore. I should just have it ignore like white space. But I'm not going to worry about that. Instead, I'm just going to make it ignore everything it doesn't recognize. So if you put in like, if I started writing like words in there, it would just ignore them. That's what we're going to do. So if it's less than, we're actually going to go back up to the top. So so this is going to be next. So we're going to jump back up to next down here. And then we will compare again AL with, this time with 9. And then if it's greater than, we also want to go up to next. And then if we have a number, then what we want to do is say, let's say, so what we're going to do is say move into dx. Well, I don't know what else is in AX right now, so I'm going to XOR dx with dx, and then move AL into move dx into dx AL. And then we'll subtract from we're going to subtract from dx 0. Okay, so this is basically subtracting off to convert this from a character into a number. Because fortunately in ASCII all of the numbers are right in a row. If they hadn't designed ASCII that way, this would be a much more complicated thing to do. Okay, cool. So then we're gonna say down here we have a function that's called read number, or a little like label that'll be read number. So here we're gonna have another loop, and the idea is let's see, read digits, accumulate into let's see, accumulate into dx. Okay. So what we do here is we're basically going to like sort of repeat this sub dx and, or, you know, sub and add and all of that stuff, but we also have to keep loading the next one out. So the first thing we're going to do is read the next character. Hey, I think we can actually like reuse a lot of this. So why don't I try and do that? Okay, cool. So what we're gonna do instead then is say, well, let me go make sure to push dx up here because we clobbered it. And then down here we want to pop dx. We have to pop in the reverse order that we push them in, or otherwise bad things will happen. So we're gonna move this like, let's see, XOR dx right before check num. And then no, we want to do okay, this isn't gonna work because, well, it sort of works, but it's a little tricky. So what we're gonna do is we still want to test it down here because the problem is we're gonna go to a different place otherwise. So basically, if it's not a digit, we're going to just return. We actually should probably stick the character back in the buffer too. So yeah, so I think for that, instead of next, we're gonna jump to return num. So return num is going to we want to subtract from, oh no. Okay, I think I just realized I got my levels of indirection wrong. So we're gonna we'll come back to that in a second. I want to finish this train of thought that I'm on right now. So we're gonna subtract from token buffer 1, and what this is doing is basically undoing this. So since we don't ever modify token buffer, we just stick it back up. We just move our pointer back, and you know, yeah, then that's that. So and then we're gonna move axdx. You know what? Let's not worry about this. Let's yeah, I don't know. No, I'm gonna leave it like this. This is just easier. So we move dx where we've been accumulating the number back over to ax where the return point is. And then we can just basically fall through into exit here because we've got our return ready. Okay. So in this part here, we know that we have a number. So we're gonna subtract from AL, we're going to subtract 0 from it. And then we're going to add to DX AL, which I don't think is actually going to be like totally legal, but we'll see. And then down here we say jump, we go back up to read number. Okay, so this should basically be your tokenizer. We can test it somewhat by checking if we get a by calling print number on it and seeing if we get the same number back. Can even make print number print out negative numbers. I think that'll be pretty good too. Yeah, I think that actually would be nice to be able to test this like for real. But let's see if we can compile. Hey, I can't believe that worked. That was a whole bunch of code. But it assembles it the first time, but it probably doesn't actually work. Okay, this I think is right. This I think is right, or this I think is wrong, actually. So what we want to do here, so token buffer is in memory. You know, we actually should probably just pull it into a register. Yeah, I'm going to do that. So we will push bx, and then we will pop bx. So we're going to use bx. That's sort of our base. So the first thing we're going to do up here is move into bx token buffer. And then down here, we can just say move, instead of moving into AL, that we can move bx. And then we can say add bx1. Yeah. Bx, and then down here we want to say add bx1. And then here we're subtracting from bx. Okay. So in exit, what we're going to do now is we want to store this value back. So we've kind of been modifying bx in place. So we're going to move into token buffer the new value of bx. Okay. So let's see if that works. Hey, it does. We want to see the thigh. Whoops. So our boot.asm file right now is oh, not .asm. We want our boot image is 633 bytes, and so what I'm checking for there is our boot sector up here only reads one sector. I think I really should have commented that, but I think this is AL here is how many sectors to read off of the disk, and so we're only reading one. So once boot.asm, or once the boot image gets up to 630 or gets up to 1024, we'll want to make sure to bump that up. If I was doing this properly, I'd add some kind of a way of saying like, oh, how big is the whole program, and make sure that that's in there. Oh, you know what I bet part of the problem is? Didn't actually include get token. Now let's try it. Hey, now we got some errors. That's what I expected. Line 66, expression syntax error for jump. Why does it? That's weird. What's wrong with that one? Maybe it's just J. I don't. I mean, like it did jump other places, so nope, that doesn't work either. Oh, interesting. So notice there it says 131, and there. So I think it's actually adding. It's like adding some value to that. So let me grab my trusty little calculator over here. So that was line 66, but it says it's line 131. So 131 minus 66 is 65. Interestingly, yeah, so I think NASM apparently just has one line or one set of line numbers, which is sort of weird that it does that. So apparently it doesn't like token buffer being, apparently that's the issue there. Oh, because of the comma, that's why. So we're getting a little bit better. One is a capitalization error. That's easy enough to fix. So 105. So 10 lines down from this, so line 50. Yeah, this is the one I thought was going to be a problem. So here's what we're going to do. We're just going to go up here and just XOR. So now I know that the top byte of AX is always going to be 0 because we don't really do anything down here to change it. So we can just move AX into DX. Like that. And then 15 lines further down. So that'll be 65 to 66 now. Oh, the same problem. So we still do ALS still just going to be 0. So let's try this. Now it works much better. Okay, let's test it out with numbers first. So we'll say test token 1 is going to be with a 0. And this should just print out 1 when we're done. Okay, so oh yeah. So here in our main program, the first thing we're going to do is say move into AX test token 1. Then we're going to say call set. I'm going to rename that to set token buffer. Okay. And then we're going to call whoops. We're going to call get token. And and then we just feed that right into print number. And so what this should do is print out number 1 when we actually go. And let me make sure that we're still, oh yeah, we're still good in our size. So QEMU. And if I scroll this up here, make it a little bit bigger so you can see how wrong it is. We got 32,768, which is not 1 in the slightest, which is kind of interesting. I wonder what's going on there. Interestingly, this is 1 in something. This is oh wait, that's 32,782. That's not even 32,768. That's really weird. I wonder what's going on here. Weird. I think, let's see, what did I set the data segment to? I set that somewhere. No, I guess not. Okay, so I think I left this all with, oh, I think what happened when we do that's a long jump there, so I think I need to set the data segment and the code segment to be the same. So let's try doing that. So let's try move whoops, that's not what I meant to do. I wanted NASM instead. Okay, so we can't move between segment registers directly, so we move CS into AX. Then we move into DS AX. Cool, and we run this. Well, now we got 32,782, or 86, I mean, so that's a different number than we had before, but still the wrong answer. So let's see what's going on. Okay, let's try getting rid of that token buffer, or not that. Let's if I don't call get token, then maybe it'll work. Nope, that doesn't work either. So that is weird. Um, wrong one. Here we go. Okay, so that's interesting. We had 32,780. Oh, right, because this is interesting. So I'm guessing that that's the address instead, because yeah. So I think 32,780. That's probably 0x8 something something something. Um, I'm guessing that's what it is. So actually, yeah. Let's 32 780 minus 32 768 is 12. Um, it looks like test token one is probably about 12 bytes away from, we've got 1, 2, 3, 4, 5 instructions. It seems pretty reasonable that would be 12 bytes. So yeah, I think that's what's going on there. Well, that's interesting. Okay, well, or no, that's not actually that interesting. That one makes sense. So maybe we're doing the same thing instead. So let's see what's going on. We set token buffer to 0. And we call get token. Oh, excuse me, I'm getting tired. Yeah, I went hiking today. I hiked Mission Peak, if any of you know where that is, but I haven't really done any kind of strenuous hiking in a while, so I'm pretty exhausted right now. But it was a good day. It was good. It was fun. Okay. Um, so we load the address of the token buffer into BX. We read the first character and advance by 1. Um, okay, so here we read a character. If it's less than 0, return the number. If it's greater than 0, we return that number. Otherwise, we subtract 0 and we add 1 to the other. And then we go back up to read number and continue. Interesting. This is where like a debugger would actually be kind of nice to have, but it's hard to wonder. Yeah, it's I don't really have access to a debugger now. I'm sure someone's kind of telling me like, oh yeah, you just do this to do QEMU, and oh man, I just noticed that Will logged in, so that's cool. So Will's a friend of mine from grad school. Good to see him there in the live stream. Glad you're able to join in, Will. That's awesome. Um, cool. Well, thanks for watching. This is pretty cool. Let me see. I'm stumped here with why is my number printer not really working out all that well, and also why my mouse disappears when I go to QEMU. I guess let's do Control G. There we go. That's what happened. I just got it grabbed. So awesome, cool. So let's see. Okay, we set the token buffer. We get the token, and let's try doing this will be kind of interesting and see if it works. So maybe what I'm getting actually is one of these first ones. So let's try instead of 1, let's try anyone that's just plus. And then I could have used the one down below actually. Why don't I do that actually? Okay, so instead of doing test token 1, we're going to do test case 1. So get token should just return the first token, which should be the token for plus, which should be -1. Since our number printer doesn't know about negative numbers, it's going to be let's see. Our token printer doesn't know about negative numbers, so it's going to print it out as a 16-bit integer, and then I'll have to do some math to get it into a negative number instead. But at least then I'll have some idea of like why I'm seeing things come out of this. So we get 32,788. I subtract off 32,768 from that, so let's see, 32,788, and we get 20. Which doesn't really match anything I was expecting there. It's almost like get token isn't actually doing anything, which it could be, you know. Yeah. Oh, it's okay. Let me run this again, and okay, so we get 32,788. What I'm going to try doing now is just commenting out these two lines, and compile, run again, and I bet we're going to get the same number, but we didn't. So that's kind of interesting. That means that something's happening. The function is doing something. So 32,782 is going to be that's we know that's the address of test case 1, so that's like in hex that's going to be 0x004 or so, something like that. So something's happening when we do this. What if I call set token buffer? Wonder which number we'll get this time. This shouldn't have any effect on what we get out of it, but well, it does actually have an effect because yeah, every time I comment this out, it changes the position of everything. So let me try and make this a little more stable. So let's see. Okay, so we're going to jump to the beginning. Hopefully that's the right number of ends in beginning. Beginning is going to be here. And we're going to move all the data up above it. So what that means is that we won't be like moving stuff around each time we recompile. Okay. Oh, that's surprising. Invalid. Oh, because I put a colon at the end of it, because assembly's really finicky about that stuff. So compile, run. Okay, so now we get 32772, which is a really interesting number to get out of it. Let me run, whoops. Oh, yeah, so we go back here. So we'll comment out each of these, and then basically I'm just trying to figure out which part of the program is going wrong right now. So we comment out each of these, and we still get 32772, which is interesting. Basically, it means the set token buffer and get token aren't doing anything. Or they're not changing AX. So that is okay. So set token buffer shouldn't be changing AX. Let's try zeroing it out just to see. And okay, so we're still back to 32772. Oh, right, because oh yeah, I wasn't calling it. I bet I always lose track of whether I've compiled this all the way or not. Okay, so when I have a set token buffer 0 out AX, we get 0 in here, and that's good. That's what we expected because I wasn't actually calling get token. So now we call get token, and then we keep going. So we get 0 again, which means for some reason get token down here is not doing anything, which is good to know. So I'm gonna leave that in there just because that I think kind of helps ground things a bit. But now we get to figure out why get token's not doing anything. This is probably where I'm gonna find out that I did something. Oh yeah, no, that's right. Okay, I was like, oh, that was probably it there. Okay, so we push our registers. We go through here. One thing I can try doing down here is just make sure we're moving to the exit point. So let's try moving into AX, our favorite number 42, and then when I run this, we should get 42 out at least. But we don't. So that's really weird. So we get 0 again. Get token is there. Oh yeah, I should have known nothing was happening because that happens. We XOR out AX in there really early. Oh, this is really stupid. I said it was going to be really stupid, but so I'm popping out AX, which means that we saved the value of AX at the beginning of our function. We did a whole bunch of stuff, and then we overrode it all with the value of AX from the function. So we don't need to save AX. I got to remember that AX is not on my list of callee save registers because it's the return value. But let's compile this, and it will probably break in a new and interesting way. So we get 65,535. That is -1 as a number, so that's working. Let's try, I've got one of the ones with multiplication, test case 2, so let's try test case 2. And there we go. Okay, so now we get 65,534. So that's one less than we got before, so that corresponds to -2. And I think now the real question is going to be, do we get number 1 back if I call my test token 1 case? This is a test token. Oops. Okay. So we compile, and then we go, and we got 1. Okay, so it looks like my code was correct. I like it when that's the case, but it takes so long to track down all these extra really kind of small issues and stuff. Let's do another test token case because we want to make sure that we can get multiple numbers out, or multiple digit numbers. So let's 42 and 0. So this should be 42. And then the other one I want to do is I want to make sure we can handle white space, because we're going to need that to be able to call this in the calculator loop actually. So we'll put a couple of spaces in there, and then we'll do 123, and then this should return 123. So I'll run this. I didn't change the test case, so but interesting, that wasn't. Oh, test token 2. We got 6. That's not 42, but it is 4 plus 2. So I skipped a step in here. But fortunately, this is easy. This is an easy fix. So the problem here is when I add to AX, I add DX. This is going to get a little bit messy. But the problem is here that I'm adding. I'm just adding all the digits together where I need the multiply, or actually up here. I need the multiply dx by 10 first. The reason that's going to be a little bit tricky is if I go over to my assembly thing, integer multiplication, it always overwrites dx. So I should have used a different register. I think cx is okay though. So yeah, here's multiply. Let's see. Actually, I think this might be okay. Well, the problem is I have to multiply into AX. But let's see. Yeah, as long as I multiply by like a small number, I think I'm gonna be okay. But so I got to rework my registers a little bit. I want to try and rework it so that instead of using AX as my temporary, I'm going to try to read that into somewhere else and then use AX as my accumulator. So the first thing we need to do is here, actually, we don't really even have to do this. So because I added the step of zeroing out AX up before, so we get rid of that, and then we change AX to, we subtract from AX to 0. That gets rid of the 0 character. BX stays the same. We don't want to load in the AL. Let's use a. Oh no. Yeah, this will work. Okay, cool. We're gonna use CL instead, because CL is not gonna get clobbered by anything else. Let's also zero out CL or CX up here. And since we're clobbering CX and we didn't push it, let's make sure we add this to our things up here. And restore it down below. All right. And okay, so where was I? 0 out CX. We read in the CL, we subtract from CL. That we add into AX, we want to add CX into that, but first we're going to multiply AX by 10. And then I think, oh yeah, we don't even have to do anything there because we just changed AX to be the accumulator now. So I think, oops, 142, but that has to be minus 76. So 142 minus 76 is 66. So that's this line. I wonder what does it not like about that? I think my dog's coming in. I heard him outside. He was like, "Oh no." Yep. Cool. Okay, so my dog's in. You can't see him though because he's not on camera. But yep. Okay. Cool. Oh right. You don't tell the register you're multiplying by. You just say multiply by 10, and it knows that it's going to be AX. So this should work then. It still doesn't work. Maybe I have to give it a size. Nope. Okay, what is my... Maybe I just can't do an immediate. Maybe that's the problem. So let's move into dx 10, and then we'll multiply ax by dx. Yeah, that one works. Now I can run it. And then we get 42 out. So that's looking good. Will says meow. Ash doesn't actually mind, our dog's Ashton. He actually doesn't really mind cats. So I don't know. He's just kind of indifferent to them, but that's good. Yes. Cool. So I got 42 out of here. And then I think since this is working, I think it should be pretty quick to write the compute function. And hopefully, oh, let's make sure that we handled the spaces as well. And so we keep running. And then we got 123 up. So I think we're good. Yeah. So cool. We have our tokenization part that took longer than I thought it was going to, but this compute part should be pretty quick. So why don't I go ahead and finish it off then? So I'm gonna make a new file here, save it as compute.asm, put like a little header, keep track of what's going on. So compute.asm is going to evaluate prefix arithmetic expression. Call set token buffer. Okay, so and this is just going to be arguments is going to be none. And it's none because I want to be able to do recursive calls on this, and it's just, you know, easier to do that without any extra arguments in it. I could probably like have like a wrapper where you put you know, you pass in the expression, a pointer to the expression you want to evaluate, and then like it sets up get token and then continues. But I don't really want to do that, so I'll just make the caller do a little bit of extra work. So here we go. We have compute, and so basically what we do is we're going to call get token. And then, oh yeah, let's do get my exit point ready. So return. We need to make sure to include. And let's see. Okay, so we call it get token. We're going to compare AX with token add. If it's an add, then we are going to call get token again. We need to save the return value from get token into somewhere. So we'll use bx. That sounds good. We call get token again. And then we add, oh, okay. We're using bx, so we have to say push bx. And then down here we have to say pop bx. We add ax and bx together, and then we can return. So we do that by jumping to exit. Okay, so there's our add case. We'll do our multiply case. So token mul. We call get token again, move into bx ax, call get token, and then add, or sorry, not add this time, we're going to multiply. So we want to multiply the thing in ax by the value in bx. So multiply by bx. That's going to clobber dx, so we need to make sure to save that. And pop it up here. And then we're done. So exit. And then finally, if we're still here, then it means we got a number out, so we didn't get anything incorrect. But yeah, we didn't get any operator, so we just got an operand. So we're just going to return that. Since that's already is an AX, We don't need to do anything special with it. And so we just kind of fall through. So I'll leave a comment here so we know what's happening. So fall through to return number. Okay. So we can just return the token otherwise. And that should basically match the, yeah, here's sort of the pseudo code that I wrote for it. So it's get token. Oh, this is not get token here. We want to call compute. There and there, there and there. Okay. Good thing I checked my pseudocode. Otherwise, that would have probably taken me like way too long to debug. So we include it in there. We're going to take a really simple function. We actually can use test token 3 because you can just use a number as an expression. So let's do NASM, run it. Oh, it calls get token still. I didn't change the call to compute, but good to know that get token still works. We'll compile, run again. We get an infinite loop now, which is actually kind of surprising. I'm surprised it hasn't like tried to crash yet or managed to crash yet. So what's going on? So one call to get token, compute. You know what? Let me try an easier case. Oops, token 2. I don't know if that case is actually easier. I think it's going to do the same thing. Yep. Oh, here's why. We have to do a conditional branch. So let's see, J&E to check mul. This is going to be check. This is why people don't write assembly language, and they made better languages because it's easy to forget to do all of this stuff. So if there's a compare, then so if it's not equal, we just fall through to return a number. So we can actually just do exit. So that's fall through and return. Okay, so this comment doesn't really matter because we can just fall through there. So that actually got simpler. Simpler and also more correct, which is the best thing to happen. So cool, we can get 42 working. Since all we're doing is calling get token, this should work also. So yep, we get 123 out, which is what we should have gotten for that. Now the more interesting cases, so like are actually like test case 1 here. So this is gonna be test case 1. Let's try that. I could just like have it do all of these at once, but I don't know. That's more work than I'm gonna do right now. Cool, so I got 3 out, which is what I should get for adding 1 and 2 together. Our test case 2 is going to be multiplying 2 and 3, so we should get 6. So that's test case 2. And yeah, we got 6 out also, so it's working. The next one should give us 46. So let's try test case 3. Oh, it would help if I reassemble it first. Okay, and we keep going, or bring that up there. We got 46, and so I think everything's working, but just to be sure, let's try one more test case. Oops, test case 5 does not exist. That wouldn't work. And we get 21 out. So I think everything is working. So cool. Well, yeah, that's what I wanted to get done for today. So that's probably a pretty good place to wrap things up. Will, thanks for joining in and watching the stream. I think there was maybe a couple of people that tuned in at various points too. So it's always good to see people join in. And yeah, I think hopefully I'll pick up next week and kind of keep building from here. the reason I decided to do this particular problem is it's a very small and manageable like subset of writing and implementing a programming language. So if you've written like small scheme interpreters or anything like that, like this looks pretty much it's you branch on the type of expression that you have, and then you evaluate arguments, and then actually apply the operator to it. So this is like the skeleton of an actual programming language implementation, but it's missing some important things like variable bindings and functions. That's the word I was looking for. I was like recursion, but it actually does do recursive expressions. Okay, but we're missing support for like functions and things like that. So I think the goal from now on is going to be to keep building this up a little bit, a little bit at a time, getting more and more functionality in there. And then in doing that, we'll be able to start writing more interesting programs faster because we don't have to do them all in assembly language and remember to get all the labels right and all of that stuff. So anyway, thanks for watching, and I will go ahead and wrap things up. I'll stay on the chat for a few minutes afterwards if you want to talk for a bit or whatever. I have nice like outro music, but yeah, that does it for now. So thanks a lot for watching, and I'll see everyone later.